We are going to start with Chapter 1, Part 1, looking at the scientific method, as well as measurement and how significant figures and scientific notation play into that. Starting with the scientific method, so let's look at the definition of the scientific method. And the definition is an organized approach to solving scientific problems. So in the science fields, as well as the mathematic fields, whenever there's a question raised and something needs an explanation to it, the scientific method is a way to approach any of those problems. So what we have here on this slide is a flow chart which explains the steps of the scientific method. It explains the approach that most scientists take when trying to solve a scientific problem. So looking at the flow chart, we're starting with observation. So this is, for example, let's use Newton. So Newton's law of gravity. So in order to come up with Newton's law of gravity, what Sir Isaac Newton did was he first observed an apple falling from a tree. So after that observation, he then moved to the second step, a question. So he saw the apple falling from the tree, observed that, and the question rose, why did the apple fall? Why didn't it float? Why didn't it go sideways, etc.? From that question then, moving on to the next step, hypothesis. So what a hypothesis is an educated guess. So why did the apple fall from the tree? Was it pulled down by some force? Was it pushed down? Was there just an absence of anything allowing it to fall? So based off the scientists' observation and their question, and using their own knowledge, they can come up with a hypothesis, why they think that observation occurred, the answer to the question that they posed. From the hypothesis then is experimentation. So whatever your hypothesis is, so say Sir Isaac Newton thought that the apple was being pulled to the ground by some unseen force. Okay, well, in order to further that hypothesis, he needed to conduct experiments to try to prove that hypothesis to be either true or to prove it false. So with the experiment, you collect data, and that's where the next step comes in, data analysis. So once you do all those experiments, you collect the data, whether it be masses, temperature changes, etc., depending upon your question. You take that data and analyze it. And when you analyze it, that data will either make the hypothesis true, which then moves it to a theory. So if that data you collect supports your hypothesis becomes a theory. And what a theory is it's similar to a hypothesis because it's an explanation. However, it's now supported by fact. So the difference between hypothesis and theory, hypothesis is an educated guess just based off of what the scientist thinks, and theory is now supported by fact. It's not just a guess anymore. However, it's not always the case where you do the experiments and it supports your theory. So sometimes it goes the other direction, and you have to come up with a new hypothesis, which requires you to develop new experiments, and you kind of move back up to this step here. Let's look at the definitions of the steps in the scientific method that we saw on the previous slide on the flow chart. So starting with observation. So how would you identify if a statement or scenario is an observation? Well, you would have to look for clues in the scenario itself, in the text. And those clues would be, are they using one of their 5 senses? For example, in the previous slide, we talked about Sir Isaac Newton and how he saw the apple falling from the tree. So he was using his sight. He was looking. So since he was looking or seeing the apple fall, that would be considered an observation. Another one would be if someone heard the mating calls of birds. They would be using their listening skill. They would be observing the mating calls of birds. From the observation, we asked the question. Now that one's pretty easy to figure out, because if they're posing a question, that's the question part. So I'm moving on to hypothesis. Now the hypothesis here is an educated guess. A more thorough definition would be an attempt to explain their observations in a common sense way. With the hypothesis, experimentation needs to be done in order to prove that hypothesis to be true or false. So the scientists would carefully design some experiments to test that hypothesis. Now, one thing we didn't mention with experimentation is the presence of a control group. So whenever the experiments are put together, a control group is usually needed. So what a control group is a group that's not subjected to conditions of the experiment. So an example of this would be if a new drug was being tested on a group of mice. Okay, so each mouse would get a different dose of the drug because they're trying to test the effects of the drug. But there's always going to be one mouse or a group of mice that is the control group, and that would be the group that didn't get any of the drug, no dose at all. So that would be the definition of the control group, and we're going to be using that in some examples as well. So know the definitions and also how to apply them to scenarios. Moving on, data analysis would be the next step. Once you conduct the experiments, you analyze the data, and these are actual measurements. Okay, masses of the sample, reaction times, any temperature readings, anything like that. From that data analysis, you come up with a result. So what was the outcome of the experiments? Did the data support your hypothesis or did it not? If it did support your hypothesis, your data supported your hypothesis becomes a theory. And all a theory is it's a hypothesis that is now supported by facts. It has the testing behind it, it has the experimentation behind it, it has the data behind it to prove it. Make sure you know the difference between hypothesis and theory. Now let's apply what we just learned about the scientific method. So we're going to take these scenarios. There are 5 of them. Some are scenarios, some are definitions, and we're going to identify what step of the scientific method is being used in each of these scenarios. So let's look at the first one. The first one is a scientist listening to the sounds a whale makes. Okay, so looking at all of the steps, you have observation, you have question, you have hypothesis, experimentation, data analysis, theory. Which one of those steps is being described with that scenario? So remember, you want to look for clues in the question itself. And what would help me figure out what step it is this word right here. The scientist is listening. So if he's listening, he's using one of his 5 senses, and we said that was an observation. So 1 would be an observation. Now let's look at the second one. We have Galileo, and we'll learn about him in this course. Initially suggesting that objects of different masses will fall at the same rate. Okay, so once again, look at all those steps, try to figure out which step of the scientific method is being shown here. What's going to help me is the initially suggesting. Okay, so what would this be? Would it be a hypothesis or a theory? Okay, it would be a hypothesis because it's using the words initially, right? His educated guess. He's suggesting, which means he doesn't know, so it's not a theory yet. He doesn't have any data to back it up yet. Okay, so number 2 would be a hypothesis part of the scientific method. Number 3, watching a leaf blowing in the wind. Once again, watching, that's one of the senses, right? We're seeing something, so that would be an observation. Number 4 should be pretty easy. Asking, there's your big clue there. Also, if they don't have the word asking, we have a question mark. Question mark would be the question part of the scientific method. Last but not least, this one's a definition, an explanation supported by facts or experimentation. And that would be a theory, which is a hypothesis supported by facts and data. So if you didn't catch those answers as I was saying them, they're all present here on this slide, and you can pause and look over those. Next, let's move on to measurements. Now this is section 1.2 in your Outstacks book if you wanted to read along at all. So when taking measurements, units are very crucial, and that's something that I'm going to point out quite often in class, as well as what lab. No matter what lab you're in, make sure you're putting on units. If the units aren't there, the measurement itself has no meaning. Because I could say, oh, 1.52. That's just a number. If I don't have a unit, it doesn't tell me 1.52 of what? Centimeters, meters, inches, because those all mean different things. So the units define what the number means. We're going to look at, when we're taking measurements, significant figures. We're going to apply scientific notation. And then we're also going to look at the definition of measurements. Lastly, we're going to look at standardization and the metric system. So we'll explore SI system, define what that means, and we'll also look at some standard SI prefixes. So this is the goal of the next part of this presentation. We're going to start with significant figures. So the definition of significant figures is the number of digits that carry meaning. Okay, so what does that mean? It means the numbers that are important. Oftentimes, students, when approaching a mathematical problem or a word problem with numbers in it, when they have to report their answer, their first question is, how far out do I go? How many digits should I report? Okay, well, we're going to look at significant figures, figure out how to identify them, and that way, whenever you are approaching a problem, you can use the numbers in the problem to figure out how many numbers or digits you should have in your answer. The reason we use significant figures is because not all numbers are exact. When you're doing calculations, the numbers involved in the calculation sometimes have varying significant figures. So we need a way to figure out which ones are important, how many we should keep, so on and so forth. Also, it's a systematic way to round a number so that everyone's having the same answer with the same amount of digits. So let's look at some rules for counting significant figures. The first rule, the leftmost non-zero number is the most significant. So what that means is, when you're counting significant figures, you always start from the left. So I'm going to start here at this 0. Now, I don't count that first 0 because what this rule just told me is the first non-zero number is the most significant. So this 0 does not count. This 0 also does not count. I don't start counting till I get to my first non-zero number, which is this number 2 right here. So the 2 is going to be significant, and then I start counting from there and keep going. Now keep in mind that anytime you have a non-zero number, so 1, 2, 3, 4, 5, 6, 7, 8, 9, it always is significant. So if the number's not a 0, it counts as a significant figure. Zeros, however, sometimes count and sometimes don't. So we need to explore that in a little more detail. So if you have a 0, looking at rule number 2, any zeros between two significant non-zero digits count. Okay, so rule 1 says that all non-zero numbers count. So that would be my 2, my 7, my 3. Those all count. Now I said zeros sometimes count. So to figure out if this 0 here counts, we look to rule 2, which says any zeros that are between two non-zero numbers count. So this 0 right here is between a 2 and a 7. So that means yes, it counts. So there are 4 significant figures in this number. Now I know this can seem a little confusing at first, but we're going to have lots of practice with it and do several problems until we get the hang of it. Let's move on to rule 3. Trailing zeros to the right of a non-zero digit only count if they are to the right of the decimal. So we'll look at some examples applying that as well. So when I say trailing zeros, I'm talking about zeros that are after that first non-zero digit. So we have a 1 is where we start counting. We start counting at the first non-zero digit. Now, the zeros after that only count if there is a decimal point present. So that's why in this first example, 10.0, all three significant figures count. All three digits count. We have a total of 3 significant figures in that number because there is a decimal point present. In the next problem, we have 1,000. Okay? How many significant figures in that number? Well, there's just one. But why? Because there is no decimal. So in order for zeros to count after your first non-zero digit, there needs to be a decimal point. Let's apply these rules to count how many significant figures are in the following. So looking at the first one, we start counting. Remember, the first rule is you start counting at the first non-zero number. So 0.03500. Which number is the first non-zero number you encounter? You always go from left to right. The first non-zero number would be this number 3 here. Okay, because I have a 0 and a 0, so those first two zeros don't count because I can't start counting till I get to my first non-zero number, which in this case is the 3. Now, does the 5 count? Yes, the 5 next to it counts because it's a non-zero number, and non-zero numbers always count. Now we have 2 zeros after the 5. To figure out if they count, we need to look at the other rules. Rule number 2 says that a 0 between two non-zero digits count. Okay, well, these 2 zeros after the 5 don't apply because there isn't a non-zero number at the end. But Rule 3 will help us decide. Rule 3 says that if there's a decimal point present, the zeros after you've started counting do count. Okay, so that means these 2 zeros count. Why do they count? Because there's a decimal point here, and we started counting at this number 3. So the first 2 zeros here and here do not count because we can't start counting till we get to the 3. The zeros at the end do count because of the decimal point and we started counting. So we have a total of 4 significant figures in this number. The 3, the 5, the 0, and the 0, all underlined in red there. So we started off with a hard one. Next one's a little bit more straightforward. So looking at this one, we first find your first non-zero digit going from left to right, and that's where you're going to start counting. So we start counting at the 2. Next we have a 1, it's non-zero, so it counts. I'm going to skip the 0 because zeros sometimes count, and I'm going to move on to the next number, which is a non-zero digit, a 2. So far I have 3 significant figures. My next job is to figure out if that 0 counts. And according to Rule 2, it does, because it is between 2 non-zero digits. It's between a 1 and a 2. So yes, it does count, and we also have 4 in this number, 4 significant figures. The next one, so once again, starting at the far left. The 1 counts because it is non-zero, the 5 counts because it is non-zero. Does that last 0 count? So we're applying Rule 3, a trailing 0. Remember, we said that zeros can count 1, either if they're between 2 non-zero digits, like the previous example, or if there's a decimal point. Do we have a decimal point here? We do not, so that 0 does not count. So there's only 2 significant figures, the 1 and the 5. In the next example, similar number, but this time notice we have a decimal point. So that decimal point, what that's telling us is that that 0 that comes after it does count. So in this number, 15.0, we have 3 significant figures. Next one, hopefully everyone gets this one. They're all non-zeros, so they all count. Last one, 70,002. So we start counting at the 7. That's a non-zero number. We know the 2 counts because that's also a non-zero number. Do the zeros in the middle count? Yes, they do, because all of those zeros are between two non-zero digits. So we have a total of 5 significant figures in that number. So the reason that we need to know how to count significant figures when given a number is because we're going to use that tool set when we're doing calculations. So whether you're doing addition or subtraction and multiplication and division, the rules are going to differ. So the first step when you are approaching a problem or a calculation, you need to look at what order of operation you are applying. So if you are applying addition and subtraction, it's a different set of rules than if you're applying multiplication and division. So let's look at those rules. For addition and subtraction, I want you first to add or subtract in a normal fashion. Okay, just do the addition, put it in your calculator and see what the answer is. From there, you're then going to count the decimal places for each number used and round the answer to the least number of decimals. Okay, so what that means is for addition and subtraction, we're not counting the numbers as a whole. We're just looking how many digits are after the decimal place. So decimal place and then on to the right. When you're counting the decimals, whichever one is smaller, that's how many you'll want to report your answer to. And we'll do a problem here in a moment so that you can see how those rules apply. Looking at multiplication and division. So if you're approaching a problem and you see that the order of operations is multiplication or division, for that you want to count the significant figures as a whole. Once again, you are picking the least. So multiplication and division, you are looking at the entire number, not just after the decimal place. You are using our tools that we used in the previous slide to count the total number of significant figures in each number used, and then you are picking the one with the least. So the difference between the two is addition and subtraction is just after the decimal place. Multiplication and division are significant figures as a whole. The thing they have in common is that you are picking the least number or the smallest number for each. All right, so let's apply those rules to some real-life examples here. So how many significant figures should the answer have for the following? So the first step, remember, is to look at what order of operation is being applied. So I'm going to go ahead and look at this first one here. We have 3.67 times 2.123. So we're using multiplication. So we're going to use the set of rules that apply to multiplication and division. And that set of rules says we're counting significant figures as a whole. So we want to look at each number that we're multiplying and count the total significant figures in that number. So the first number, 3.67. Well, they are all non-zero numbers, so they all count. So we have 3 total significant figures in that number. The number we're multiplying it by is 2.123. Once again, they are all non-zero numbers, so they all count, giving us a total of 4 significant figures. Now remember, we're picking the number with the least amount of sig figs. So which number is smaller, 3 or 4? And the answer is 3. So that means we want our answer to be 3 significant figures. So 3.67 had 3 significant figures, 2.123 had 4 significant figures. 3 was smaller, so that means we want 3 significant figures in the answer. So to do that, we're going to go ahead, start counting in the far left. 1, 2, 3. So those are the only 3 digits you want to represent. You do not want the rest of those. So the correct answer with the correct amount of significant figures is 7.79. Let's try the next one. So the next one, first thing we want to look at is what order of operation is being applied, and in this case it's division. So it's going to be the same rules as the multiplication one we just did. We're going to go ahead and count how many significant figures are in each number. We get a total of 3 for 1.52, and then we're dividing by 2, and that's just 1 significant figure. You pick the smaller of the two. In this case, 1 is smaller than 3. So we want our answer to just be one significant figure. Now, when we put this in our calculator, we get an answer spit out that says 0.76. Okay, now that's two significant figures, so we don't want to report both of those. We only want to report one significant figure. So how we do that is we pick the first number we see going from left to right, and that's going to be that 0.7. Now you always want to make sure that you look to the number next to it, because if the number is 4 or less, that would stay a 7. However, if the number next to it is 5 or more, you need to round up. So in this case, it's a 6. So that means that 7 is going to become an 8 to give us a final correct answer of 0.8 to one significant figure. All right, let's try the next one. So the next one is addition. So we haven't done one of those yet. Different set of rules. So remember, for addition, we're not looking at the significant figures as a whole. We are looking just after the decimal place. Okay, so let me find a slightly different color here. So looking at the first number, we're going to go ahead and count how many places under the decimal. So for 0.125, we have 3 decimal places. Okay, the next number, 2,112.13. Okay, we're not counting that 2,112. Those don't matter, because since we're adding, we're looking at just how many spaces after the decimal, and we only have 2 after the decimal. Put D there, kind of hard to write. All right, and then 25.00. Now, these 0.00, those count even though they're zeros because they're after the decimal place. So we have 2 decimal placeholders in that one as well. And then the last one, we're looking just after the decimal place, and we just have 1 number after the decimal point. So looking at the numbers we wrote, we have a 3, a 2, a 2, and a 1. So we pick the smallest. So that's going to be 1. So what that means is we want to report our answer to go out 1 decimal place. So when we add all of this together, our calculator is going to give us this answer here. Now this is not to the correct amount of significant figures, so that's why we're doing the counting, so we can figure that out. So we're going to report this whole section here, the 2,140, and then we're going to go out 1 decimal place. So just to where this 3 is. So that means we don't want the 5 and the 5 reported. But you have to make sure that you always look to the number next to it and round up if needed. In this case, after the 3 is a 5, so that 3 is going to become a 4 to give the final answer of 2,140.4. So we went out 1 decimal place, but the total amount of significant figures is 5, because all 5 of those numbers count. Now here are some more problems that you can try on your own, and we'll also be doing them in class. If you are not choosing the in-class option, you will have access to me working all of these problems via video. So next we are going to go into scientific notation. So for scientific notation, it's a way to represent a very small or a very large number. So if you have a number in the order of millions or trillions or billions, you don't want to have to write all of those zeros out. So this is a shorthand way to do that by raising it to a power of 10, representing each to a power of 10. So what I mean by power of 10 is we're looking at 10 to the first power, or 10 to the second power, 10 to the third, so on and so forth. So let's just look quickly at how this is done. Okay, we have a set of rules we'll apply in a moment here, but I just wanted to show you a quick example. So if you had the number 4,520, This is the normal notation of writing it, which means it's just our everyday way that we're used to writing numbers. If we wanted to write that in scientific notation, it would look like this over on the right-hand side. Okay, notice we have a decimal point here now between the 4 and the 5, and we have 10 raised to a power after. And we'll talk about what these numbers mean and how we figure out what this exponent is going to be. For this small number, so 0.000671, that's how we would write it in normal notation. Now in scientific notation, once again, it's going to be represented, we'll have a decimal point, and then it'll be raised 10 raised to a power, in this case -4. So we're going to talk about all these aspects, how to figure out where the decimal point goes when we write it in scientific notation, as well as how we get this exponent. How do we get this little number up here? Why is it 10 to the -4th? And we're also going to discuss why are some negative, like in this bottom case here, and why are others positive, like on the one up here. So let's take a look. Let's first look at how to tell if that exponent is going to be positive or negative. So there are some examples shown here. So in this first example, I have 1 times 10 to the positive 1. That's the scientific notation of the number. If I were to write that in normal notation, I would get 10. I do this by moving the decimal point 1 to the right. And we'll go over those specific rules in a minute here. But what I wanted to point out was that if you have a positive exponent, like here, 10 to the positive 1, the normal notation version is always going to be greater than 1. In the very bottom example, I have 1 times 10 to the -1, so this time I have a negative exponent. And if you have a negative exponent, the normal notation version is always going to be less than 1. So that's why I get 0.1. The middle example, if you ever see a case where it's raised to the 0 power, it's just that number by itself. So the takeaway that I want you to get from this slide is if a number is less than 1, it's going to have a negative exponent. If a number is more than or greater than 1, it's going to have a positive exponent. So some things to remember when going from normal notation to scientific notation are listed below. So first off, when you are given a number in normal notation, so let's look at the number at the very bottom of the slide here, 29, what is that, 29 million? So that's the normal notation version. So if I wanted to take that number and write it in scientific notation, I'm going to apply this first rule here. And what that first rule says is I want one significant figure to the left of the decimal. What that means is you want one non-zero number to the left of the decimal. So looking at that number, 29 million, I know that I'm going to want my decimal point between the 2 and the 9 when I write it in scientific notation. Because that way I have just one non-zero number to the left of the decimal point, being the number 2 in this case. All right, next, how do I figure out what the exponent's going to be? So I'm going to look to rule 2 here to apply that. The exponent is going to be the number of places that you had to move in order to get the decimal where it is. So the original number, 29 million, doesn't have a decimal point in it. It just has commas. So if there is no decimal point present, you start at the end of the number and then move your way all the way over until you get it between the 2 and the 9. So let's count how many times we're going to have to move this decimal to get it between the 2 and the 9. So I've moved it twice so far, 3 times, 4 times, 5 times, 6 times, 7 times. So I had to move that decimal 7 times to get it between the 2 and the 9. So that's where this number 7 comes, the exponent 7. Now, the third rule, let's explore that.
how do we know if that exponent stays positive or if it needs to be negative? And that's what we explored on the previous slide. Remember, we said that the exponent's going to be positive if the original number in normal notation is greater than 1. Another way to look at that is if you move the decimal, what direction did you move it? So your exponent will be positive if you had to move that decimal to the left, which we did, right? We started at the end of the number and we kept moving all the way to the left till we got between the 2 and the 9. So 29 million, huge number, much greater than 1. So we know that this exponent needs to stay a positive 7. Now, lastly, the last rule says only significant figures are kept. So make sure when you are representing in scientific notation that you're looking at the significant figures as well. So you want to use the original number in normal notation, count how many significant figures are in that number, and keep that same amount of significant figures in the scientific notation version. So in the original number, we said there was no decimal point, right? We had to create one at the end to know how many spots to move it. So since there was no decimal point, the 2 was significant because it's the non-zero number. The 9 is significant because it's also a non-zero number, but none of these zeros counted towards significant figures because they're trailing zeros with no decimal point present. So there were only 2 significant figures in this original number, so that's why when we write it in scientific notation, we have just 2 and the 9 present, 2 significant figures once again. Now keep in mind that this times 10 to the 7th does not count at all towards significant figures. This is just representing how many times we move that decimal point. It's only the numbers before the multiplication sign that count towards significant figures. So let's try again, applying it to this next problem, 0.00033303. All right, so let's go to the first rule once again. The first rule saying we want one significant figure to the left of the decimal. So where do you think the decimal point should go in this number? Obviously the answer is there, so you can already see, but it's going to go between the 2 3's because that will have just one number to the left of the decimal. Now next, to figure out the exponent that we have here, 10 to the negative 4th, we get that 4 by how many times we had to move the decimal. So in this case, it does have a decimal point, so we just start where the original decimal is, and we're going to move 1, 2, 3, 4 times to get it between those 2 3's. So that's how we get an exponent of 4. Now the reason why that exponent's negative 4 and not positive 4 is due to the rule up here. We said that exponents are going to be negative if the original number, normal notation, was less than 1. And 0.0003 was the original number, and that's definitely less than 1, so we needed a negative exponent here. Another way to look at it as well is what direction you move the decimal. So if you had to move it to the right, it's going to be a negative exponent. So whichever one's easiest for you to remember, both work. And we indeed moved it to the right, so that's why it's negative. Last but not least, significant figures. Make sure to check those all the time. We start counting our significant figures at the first non-zero digit, so that would be this 3 right here. So that's significant figure number 1. The next 3 counts because it is a non-zero number. We also know this 3 at the back counts because it's a non-zero number, and we just need to figure out if that 0 counts, because those are the ones that sometimes count and sometimes don't. And in this case, it does count because it's between 2 non-zero numbers and it's after the decimal point and we already started counting. So notice if you count those purple circles, I have 4 of them, so that's why I have 4 significant figures in my answer. So going from scientific notation to normal notation. So the previous slide, we were given normal notation numbers, and I showed you how we put them in scientific notation. Well, we're also going to need to know, if we are given them in scientific notation, how to get them back into normal notation. Okay, so there's a few things to remember when you are doing that. You need to keep count of your significant figures, never forget about those. To figure out what the normal notation would look like, you're going to look at the exponent present, what power is it raised to, and you'll move the decimal point that many times, so it's just the reverse of what we just did. Remember, once again, a little review here, right? Positive exponents, you're going to move to the right so that the number gets bigger. Positive exponents mean big numbers. If you have a negative exponent, you're going to move to the left, and you want to have the number get smaller. Negative exponents are numbers less than 1, so the number needs to get smaller. You'll also need to add placeholder zeros depending upon the problem. So we'll work through several of these examples in class and on videos so that you can see step by step and get some more practice. So here are some examples for you to try on your own, applying the principles we just talked about in regards to scientific notation. Make sure you are paying attention to significant figures. These problems will be worked through in class, and a video of some worked problems will also be provided. That is the end of part 1 of chapter 1.